In a half-wave rectifier, only half of the input alternating current waveform is converted to direct current. This means that the average output voltage is only half of the peak input voltage. However, the effective power output can be more than 50% of the input power due to the following reasons. Firstly, non-sinusoidal waveform. The output waveform of a half-wave rectifier is not sinusoidal but rather a pulsating direct current waveform. This non-sinusoidal waveform contains harmonic components, which increase the effective power output. Secondly, reactive power compensation. In alternating current circuits, reactive power is consumed by inductors and capacitors. In a half-wave rectifier, the inductive reactance of the transformer winding and the capacitive reactance of the filter capacitor cancel each other out, reducing the reactive power consumption and increasing the effective power output. Thirdly, peak current and root mean square voltage. The peak current flowing through the circuit is higher than the root mean square current, which is used to calculate the effective power. This higher peak current contributes to an increase in the effective power output. The effective power output of a half-wave rectifier can be calculated using the following formula: P average equals voltage peak divided by 2 times the square root of 2 times current peak, where voltage peak is the peak input voltage and current peak is the peak output current. Assuming a sinusoidal input waveform, the effective power output can be expressed as P average equals 0.637 times voltage root mean square times current root mean square, where voltage root mean square and current root mean square are the root mean square input voltage and current, respectively. Consider a half-wave rectifier with an input voltage of 120 volts root mean square and a peak input voltage of 169.7 volts, that is, 120 times the square root of 2. If the peak output current is 10 amps, the effective power output becomes P average equals 0.637 times 169.7 volts times 10 amps equals 1093.4 watts. Therefore, the effective power output of the half-wave rectifier is approximately 91%, that is, 1093.4 watts divided by 1200 watts of the input power. The effective power output of a half-wave rectifier is typically less than 100% due to losses in the circuit components, for example, the diode, transformer, and so forth. Let's delve deeper into the workings of a half-wave rectifier and the factors influencing its effective power output. To fully grasp the concept, we'll explore the underlying principles and provide a comprehensive explanation. A half-wave rectifier is a fundamental electronic circuit that converts alternating current to direct current. It allows current to flow in only one direction, effectively blocking the negative portion of the alternating current waveform. This process results in a pulsating direct current output which, while not a smooth direct current signal, is a crucial step in many electronic applications. The average direct current voltage of a half-wave rectifier is approximately 0.318 times the peak alternating current voltage. This value is significantly lower than the peak voltage because only half of the alternating current waveform is utilized. The remaining half is blocked by the diode, leading to a considerable reduction in the average direct current output. However, the effective power output can be more than 50% of the input power, and this is where things get interesting. The non-sinusoidal waveform of the rectifier output plays a significant role. Unlike a pure sinusoidal wave, the output of a half-wave rectifier is a pulsating direct current signal with sharp peaks and abrupt transitions. This waveform contains harmonic components, which are multiples of the fundamental frequency. These harmonics contribute to the overall power content of the signal. While the average direct current voltage is reduced, the presence of these harmonics increases the root mean square voltage, which is directly related to the effective power. Reactive power compensation is another key factor. In alternating current circuits, reactive power is associated with energy stored in inductors and capacitors. Inductors store energy in a magnetic field, while capacitors store energy in an electric field. This stored energy oscillates between the source and the load, without performing any actual work. In a half-wave rectifier, the inductive reactance of the transformer winding and the capacitive reactance of the filter capacitor can interact in a way that reduces the overall reactive power consumption. When the inductive and capacitive reactances cancel each other out, the circuit becomes more resistive, leading to a higher power factor. This improved power factor results in a more efficient transfer of power from the source to the load, increasing the effective power output. The peak current and root mean square voltage are also important considerations. The peak current in a half-wave rectifier circuit is the maximum instantaneous current that flows through the diode during each cycle. This peak current is higher than the root mean square current, which is the effective current value used for power calculations. The higher peak current contributes to the overall power delivered to the load. Additionally, the root mean square voltage of the non-sinusoidal waveform is higher than what would be expected based on the average direct current voltage. This increased root mean square voltage further enhances the effective power output. To calculate the effective power output, we use the formula P average equals voltage peak divided by 2 times the square root of 2 times current peak. This formula takes into account the peak values of voltage and current, which are crucial for determining the actual power delivered. For a sinusoidal input waveform, the effective power output can be expressed as P average equals 0.637 times voltage root mean square times current root mean square. This formula is useful when the root mean square values of voltage and current are known. Let's consider an example to illustrate these concepts. Suppose we have a half-wave rectifier with an input voltage of 120 volts root mean square. The peak input voltage would be 169.7 volts, calculated as 120 times the square root of 2. If the peak output current is 10 amps, the effective power output can be calculated as follows: P average equals 0.637 times 169.7 volts times 10 amps equals 1093.4 watts. In this case, the effective power output is approximately 91% of the input power, assuming the input power is 1200 watts. It's important to note that the effective power output is typically less than 100% due to losses in the circuit components. Diodes, transformers, and other components dissipate some energy in the form of heat, reducing the overall efficiency of the rectifier. Furthermore, the calculations above assume ideal conditions. In reality, factors such as diode voltage drop, transformer winding resistance, and capacitor equivalent series resistance can further reduce the effective power output. In summary, the effective power output of a half-wave rectifier can be more than 50% of the input power due to a combination of factors including the non-sinusoidal waveform, reactive power compensation, and the relationship between peak current and root mean square voltage. Understanding these factors is crucial for designing and analyzing rectifier circuits in various electronic applications. The half-wave rectifier, while simple in design, presents a complex interplay of electrical characteristics that influence its performance. By examining the factors that contribute to its effective power output, we can gain a deeper appreciation for the intricacies of alternating current to direct current conversion. Consider the implications of these principles in practical applications. For example, in a power supply circuit, the efficiency of the rectifier stage directly impacts the overall efficiency of the power supply. By optimizing the design of the rectifier, engineers can minimize power losses and improve the performance of the entire system. Similarly, in renewable energy systems such as solar power, rectifiers play a crucial role in converting the alternating current output of inverters to direct current for battery charging and other applications. Understanding the factors that affect the effective power output of these rectifiers is essential for maximizing the energy yield of the system. Furthermore, the harmonic content of the rectifier output can have implications for other electronic devices connected to the same power grid. Harmonics can cause interference and distortion, potentially affecting the performance of sensitive equipment. Therefore, it's important to mitigate harmonics through proper filtering and design techniques. In conclusion, the effective power output of a half-wave rectifier is a multifaceted topic that involves a combination of electrical principles and circuit design considerations. By understanding the factors that contribute to its performance, engineers can optimize rectifier circuits for a wide range of applications, improving efficiency, reducing power losses, and ensuring reliable operation. Let's consider how these concepts extend to other types of rectifier circuits, such as full-wave rectifiers and bridge rectifiers. Full-wave rectifiers utilize both the positive and negative portions of the alternating current waveform, resulting in a higher average direct current voltage and a smoother output compared to half-wave rectifiers. Bridge rectifiers, a type of full-wave rectifier, employ 4 diodes in a bridge configuration to achieve full-wave rectification. These rectifiers offer improved performance and efficiency compared to half-wave rectifiers, making them suitable for more demanding applications. The principles of non-sinusoidal waveforms, reactive power compensation, and peak current considerations also apply to full-wave and bridge rectifiers. However, the specific impact of these factors may vary depending on the circuit configuration and component values. For example, the harmonic content of the output waveform may be different in a full-wave rectifier compared to a half-wave rectifier. Similarly, the reactive power compensation effects may be more pronounced in certain circuit designs. Understanding these nuances is crucial for optimizing the performance of different types of rectifier circuits. Another important aspect to consider is the selection of appropriate diodes for rectifier applications. Diodes are semiconductor devices that allow current to flow in one direction while blocking current in the opposite direction. The characteristics of the diode, such as its forward voltage drop, reverse leakage current, and switching speed, can significantly impact the performance of the rectifier circuit. Selecting diodes with low forward voltage drop and fast switching speeds can minimize power losses and improve the efficiency of the rectifier. Additionally, the diode's reverse voltage rating must be sufficient to withstand the peak reverse voltage that occurs during each cycle. Over-exceeding the diode's reverse voltage rating can lead to device failure and circuit malfunction. Furthermore, the thermal management of diodes is critical in high-power rectifier applications. Diodes generate heat due to power dissipation, and excessive heat can damage the device and reduce its lifespan. Proper heat sinking and cooling techniques are essential for maintaining the diode's operating temperature within its specified limits. In addition to diodes, other components such as transformers, capacitors, and resistors also play a crucial role in rectifier circuits. Transformers are used to step up or step down the alternating current voltage to the desired level. Capacitors are used to filter the output waveform, reducing ripple and providing a smoother direct current voltage. Resistors are used for current limiting and voltage division purposes. The selection of appropriate component values is critical for achieving the desired performance characteristics of the rectifier circuit. Moreover, the layout and wiring of the rectifier circuit can also impact its performance. Stray inductance and capacitance can introduce unwanted oscillations and noise into the circuit. Proper grounding and shielding techniques are essential for minimizing these effects and ensuring stable operation. In conclusion, the design and analysis of rectifier circuits involve a complex interplay of electrical principles, component selection, and circuit layout considerations. By understanding these factors, engineers can optimize rectifier circuits for a wide range of applications, improving efficiency, reducing power losses, and ensuring reliable operation. The principles discussed here provide a foundation for further exploration of more advanced rectifier topologies and techniques. As technology continues to evolve, new and innovative rectifier designs will emerge, offering improved performance and efficiency for various electronic applications.